The next question, please. Come on, there. Oh yeah, come on. You take that microphone.
Yeah.
You ask the question to who?
To Professor Hiratis.
Oh.
It was the last talk.
You're getting our street star today. Yeah.
You promoted the laser ablation technique as something which is very easy to use and you can have a high throughput method, but then you introduced us to the laser ablation in liquid, and that did not seem, to my account, as a very fast method as it's kind of an offline method. Have you any ideas putting it into more faster method?
Okay, basically the gel chemistry. I don't care about the throughput. Okay, for example, the time consuming, we don't care. So important point is how we get the very good data. This is very important. Because the number of samples limited, for example, nationwide, is quite limited. So the most important point is the data quality. The time is the matter. So the concept of lab is what is extreme high sensitivity detection for the in situ analysis. Okay? In the case of the laser ablation, we can separate the isotope interferences or many for the atom interferences. So in the case of the isotopic analysis, laser ablation ICP is not the best, sometimes best solution. So the important point is chemical separation is very important. Okay, maybe you don't like. Okay, so the lab is not our invention. This is commercially already 10 years ago. It's an industrial technique for the production of the nanoparticles. So many industrial people using nano technique, but that's not for the chemical analysis. They're producing the nanoparticles. But for example, in our field, some samples, for example, platinum bearing samples in the meteorite, it's quite difficult to dissolve. Okay, but after the lab sampling, all the sample is now changed to nanoparticles. That is much easier to decompose in acid. So easy decomposition and easy for the separate chemical separation and purification procedures. So this is the beauty of the lab technique. But this is not high throughput. But for some special cases, we can use lab technique combined with other mass spectrometers.
Yeah.
So answering your question.
I was just thinking about having something like an online technique, then you would maybe also be able to get some special resolution out of it, which is now not possible.
Yeah, that's right, yes. So now we can choose to take one, for example, integration of small samples. We can choose two approaches. One is galvan optics. The other is lab. The both techniques we can accumulate or integrate them from a separate ablation pair. So we can choose if we need some chemical separation or purification procedures, lab is better. But if there's no need for the chemical separation, the galvan optics much faster and powerful, and also contamination much smaller. So we can choose galvan or lab. This is better.
Okay, thank you.
The next question, please.
我要这么问吧，就是我想问那个史蒂文瑞，就是在那个blue discharge 里面的那个偏血值的那个分析结果。
It's to Stephen, yeah.
How pH value to affect electrical result?
The pH value.
pH value of the solution.
Oh, excellent question. And you are entitled to candy. As it turns out, lower the pH, higher the atomic emission. So we see higher proportion of atom formation as we go down, say, from pH 2 to about pH 1 tends to be a standard solution. And we think that has something to do with the amount of current that's dropped near the cathode surface itself. We've done imaging, atomic emission imaging type of studies and looked at the density of emission as spatially as well as wavelength selective. What we found is that the atomic emission is brighter, closer to the cathode as the pH goes down. So the solution, it will run as long as the solution is conductive. You can do this on tap water, you can do this on salt solutions, you can do this on basic type of solutions with, it will still work, but the sensitivity is less.
If the pH rate is different, so how
typically what we do is take a sample of interest and then we add it to a low pH solution in the mixing step. In a typical field analysis, that's how it would be done. So you'd actually have to carry around your concentrated solution of nitric acid and let it run. But that's, you know, a typical 1 liter bottle with something like this might run for maybe a day and a half before it comes out.
I have another question for Mr. Stevens. Yeah, I noticed in your slide imagine this distribution, right? Use JAAS. I want to know, can you use this method for small size sample?
That's an excellent point. Yes, in fact, you can do things on, say, combining low discharge optical emission spectroscopy with micro. Now, you are limited to the best spatial resolution that you can get, and that brings in an interesting point. The spatial resolution is based, or is dictated by the gas pressure in the cell, the mean free path, as well as the time the pulse is on for discharge. The best resolution that we've been able to get in the DC pulse is on the order of about 25 micrometers for width half max. Radio frequency, because of the requirement to charge the surface before we create the glow discharge, is more on the order of about 150 to 200 micrometers. So taking that into account and using the same kind of idea where we just change the focal lengths to create magnification, you could do microscopy. Or one thing that I didn't talk about was our ability to look at really large samples. So on the order of about 10 square centimeters is the biggest that we can do right now.
Okay, thank you.